Hello, I am Jet Carbofuel from Group Makgeolli and here to discuss the laboratory activity, which is about impulse response. For this activity, the goal is to create a sampling rate compression using MATLAB, wherein the LTI system response is being used for, in theory, the response of an LTI system when a unit impulse sequence is given as an input is denoted on this example. The given signal is the x of t and the LTI system is the h of t and the output is the y of t. And for the formula, it is the multiplication. And another thing is from the time is the x of n if there's the given time n, and the system has the LTI system has the h of n and the output would be y of n. Almost the same at the given previous diagram. And here we have the code for creating a impulse response. There are two responses on this laboratory experiment would be the first order system and the second order system. The parameters would be a value and b value, which is this for the b200, for the a 1 negative 0.9 and 0 for the first order system. And for the second order system, it is for the B is 100 and for the A 1 0.6 and 0.8. The N is constant at 0 to 10, 0 colon 10. For the laboratory questions, we have answered the following questions. What is impulse response? It is the where the output signal is presented with a brief input signal, and it is the reaction of the dynamic system in response to some the external changes that happen in the system. An LTI system is where a class of system and signals that are both linear and time invariant. Outputs for the linear combinations of the input are the same as the linear combinations of individual responses to those inputs. Time invariant systems are systems where the output does not depend on what on when the signal is applied. And lastly, the convolution, the mathematical way or method for combination of two signals to form a new or the third signal. The most important method in digital signal processing, and it basically the framework or the backbone of the mathematical aspects of DSP. And now for our outputs, as you can see, we have used the same codes on the given above, these codes. And we have inputted two set of samples. The set A would be the given values and the set B are the groups values. The group have tweaked some of the values on the parameters A and B for the impulse response of the first order system and the second order system. Zooming in, as you can see on the A, we have the same set of values for the B, A of the first order system and the second order system. And for the B, the group has tweaked some of the values, for example, from the B parameter. Actually, it is all of the values. We have changed a lot of values so that we could see some of the differences between the two given outputs. And after executing the program, there is no command window output and it is directly on the waveform. On the A, the graph shows a more downward data points graph with starting from 2 amplitude going going down up to 10n, or the length is 10. And for the second order system from the set A, it shows a almost inverted outputs where there are negative amplitudes and there are also positive amplitudes. And it is like a pattern where there are two, then one, two values, and you can form a when you try to form a graph, you could line up the graph like this. And now to see the differences after tweaking the values of B and A for the first order and second order impulse response, you can see the differences on the output on the first order system. On this, it is a decreasing amplitude where the signal's behavior is somewhat a sinusoidal pattern if you try to connect the signal, and it is decreasing in amplitude as it increases the n. On the second order, it is more of a alternating amplitude per n as n increases, and the amplitude is leaning towards more negative side as there are less data that are in the positive amplitude. And also, you can see a pattern for the sinusoidal where it goes down, then up, down again, then up, and down again. If you try to connect the sinusoidal, the data points for the graph. And in here, you can compare that um, on the system if there are changes on the inputs and there's an immediate changes on the outputs. Since the changes are only on the A and B parameter and not on the n, since the n isn't constant from 0 to 10, you can see the changes on the plotting and the amplitude of the data points per each increase in n. For the analysis, it is discussed earlier that on the differences on the parameters in input A and B, the set A and B are in this form. And you can see the changes in the graph on the first order and second order and could compare it to the another set since there are tweaks or changes on the parameters A and B for each given code for the LTI response. And for the conclusion, the entirety of the LTI system could be described by impulse response, where if there are arbitrary inputs, the output would be the convolution of the given signals, with the impulse response coming from the system itself. The impulse response of an LTI system can be described and predict the output through calculation of the response of the LTI system with the given arbitrary input from the impulse response using convolution. With that, the outputs of an LTI system could be calculated from the input and the impulse response coming from its inputs. And that sums up the laboratory experiment 16, which is about LTI response, impulse response by Makgeolli group consisting of Jet Carbopiol, Adrian Ilagan, Philip Pinello, and Joshua Tadeo. Thank you.